All right, everybody. So, last video we talked about differentiating exponential functions. Now, let's hit the flip side of that coin and talk about differentiating logarithmic functions. To begin, let's start off with the derivative of the natural logarithm. So, the derivative with respect to x of the natural log of x is equal to 1 over x for x greater than 0. Why this restriction for x greater than 0? Because the domain of the natural logarithm is only positive numbers, right? It doesn't make sense to take a derivative at a place where the function itself doesn't even exist. However, what is true is that the derivative with respect to x of the natural log of the absolute value of x is also equal to 1 divided by x. And this is true for all x as long as they are not 0. So that's kind of fancy, right? And it's 1 over x, not 1 over the absolute value of x. But as long as you put these absolute value bars on to make sure that everything that's not 0 is in the domain, then you can extend the rule a little bit further. We'll prove the first case. Because unlike the exponential function, which you actually need to use the limit definition to prove that one, and it takes L'Hopital's rule. This one actually follows from the formula for the derivative of the exponential function. So, let's let x be greater than 0, and let f of x equal the natural log of x. Then, e to the f of x is equal to e to the natural log of x. Right? Makes sense. We have f of x equal to the natural log of x, so e to the f of x is equal to e to the natural log of x. E and natural log cancel when you have an exponentiation. Remember, not multiplying around here, only exponentiating. They cancel, and you get x. So now we're going to use a trick that is going to look kind of similar to implicit differentiation. If we have these two things equal, their derivatives must be equal. Evaluating both sides, derivative of x is just 1. This, we already know. It's equal to e to the f of x times f prime of x. But f prime of x is what we want. We wanted the derivative of the natural log. So let's solve for f prime of x. F prime of x is now 1 divided by e to the f of x. But what was e to the f of x? It was x all along. And so now we've proved exactly what we set out to. For all positive x, the derivative of the natural log of x is 1 divided by x. Fancy. I won't make you guys have to know that, but I think it's valuable to see. Alright, now that we have the rule, let's use it and compute a few derivatives. Okay, let's say f of x equal to x times the natural log of x. And for b, let's say g of x is equal to the natural log of x divided by x cubed. Alright, so see if you can try these just using the rule on your own, and then we'll do them together. Alright, welcome back. Hopefully you've given those a good try. F prime of x. I see that we're multiplying two things together, meaning, hey, we need to use the product rule. So the first one times the derivative of the second plus the second one times the derivative of the first. So that's x times 1 over x plus derivative of x is just 1, so we're going to have plus natural log of x. It's the sense of just being natural log of x plus 1. Kind of fancy. The fact that there are no x's left over in that. Cool to me. Alright, let's do part B. Part B, there's two ways. You could view it as x to the negative third times the natural log of x and do it that way using the product rule, which you can do. For the sake of showing it, let's do the quotient rule. G prime of x is bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Alright? That'll give you x cubed divided by x minus natural log of x times 3x squared divided by x to the 6th power. If we continue on a little bit further, we can simplify. It's equal to x squared minus 3x squared natural log of x divided by x to the 6th power. Right, just canceling x cubed over x becomes x squared. And now I see some common factors of x on the top and bottom. So this will be equal to 1 minus 3 natural log of x divided by x to the 4th power. And that's where I'll care to leave that. You'll notice that this is probably the closest formulation to what you would get if you did it via the product rule, because you could split this up and it would be x to the negative 4th minus 3x to the negative 4th natural log of x. So, either way, it'll work out. So what does the chain rule tell us now? What if I have the natural log of an arbitrary function and not just a normal one? Chain rule says that the derivative with respect to x of the natural log of the function, of some function of x, doesn't matter what f of x is, will be f prime of x divided by f of x. Alright? And for those of you who don't believe me on this, let's prove it with the chain rule. Let's let u be f of x, since that's a kind of our inside of this thing, and y equal natural log of f of x, aka natural log of u. Your very own natural log. Not to be confused with your unnatural log. Or your semi-natural log. Neither of the other two exist in math, but I'm a mathematician, I make bad jokes. It's my job. Half my job. Okay, let's continue further. We want the derivative with respect to x of natural logarithm of x, aka we want dy dx. Which the chain rule says is dy du times du dx, which is equal to, okay, we know that the derivative of the natural log of u with respect to u is 1 divided by u. And then for, goodness graciousness, words escape me. For the derivative of u with respect to x, well, we don't know what u is, right? It's just some arbitrary function f of x, which means its derivative is just f prime of x. Substituting back in for u gives us f prime of x divided by f of x, exactly as we stated. And this is true for all values of x for where f of x is positive, right? Because otherwise the domains don't match up. Not a big concern in this class. Let's do an example. Compute the derivative of f of x equal to the natural log of x cubed minus 3x plus 4. Alright, sounds like a hairy ordeal, but by this formula, not bad at all. F prime of x will just be, and again, not the same f of x, right? Here, this is the f of x in that formula. F prime of x will be the derivative with respect to x of x cubed minus 3x plus 4, derivative of the inside, just divided by the inside. And derivatives of polynomials are nice and easy to find. This will give us 3x squared minus 3 divided by x cubed minus 3x plus 4. No pain, no struggle. Just logarithms. Alright. We can also sometimes use logarithm rules to simplify things when we calculate derivatives like this. What do I mean by that? Well, for example, let's let g of x equal the natural log of x cubed plus 7 squared times x to the 4th minus 7 all to the 5th power, and that's it. And we want to find g prime of x. Alright, how do we do this? Well, we could do it kind of a hard way, right? There's two kind of harder ways we could do it. We could multiply that whole thing out to get some big, nasty polynomial of degree 26. So we're not going to do that. Or we could try to do it just brute force like this and use the chain rule twice when computing this interior derivative as well as the product rule. Doable, but still kind of sucks. Or we can use properties of logarithms to make this problem a lot simpler. Let's recall g of x itself we have the logarithm of two things multiplied together. Our logarithm laws tell us that's the sum of each of the two logarithms individually. Okay. Looking better. We can now chain rule each individual part, right, to take those interior derivatives, but it gets even better. Exponents pull down in front of logarithms. So this is really 2 times the natural log of x cubed plus 7 plus 5 times the natural log of x to the 4th minus 7. And both of these are now easy to compute the derivatives of the inside. So g prime of x will equal, we know what the derivative of natural log of a function is, 2 times derivative with respect to x of x cubed plus 7 over x cubed plus 7 plus 5 times derivative with respect to x to the 4th minus 7 divided by x to the 4th minus 7. That's a one-step simplification. You'll end up with 3x squared times 2 is 6x squared plus 7 goes away. 4x to the 3rd, the minus 7, oh it is 7 both times, goes away, and you're left with 5 times 4 is 20, x cubed over x to the 4th minus 7. You can merge the two fractions back if you want. I don't see the need to. And it would in fact just kind of get you back where you started. Alright, let's do another example. Your book talks about something called logarithmic differentiation. This is not quite the same as that. This is using logarithm laws to our advantage. Your book talks about, hey, we're going to introduce a logarithm where it wasn't there before and then use that. And yeah, you could. Like, I'm not going to argue that like it's a thing you can do. For those of you who didn't hear what I said, your book has a whole section called this. Not a whole section, but like a subsection called this. I think it's absolutely useless. Because in my entire math career, I didn't even learn about it until I started writing my lesson plan for this this course. I was like, okay, what does the book actually talk about? And yeah, if it hasn't come up for me, there's no reason that you guys should need it. So I'm not going to assign problems on that. Alright, let's do another example that's like this though, where if we already have a logarithm, we can exploit what's already there. Let's let f of t equal natural log of t cubed e to the negative t. And we want to find f prime t. So again, you could do it the brute force way where you say, okay, it's the derivative of this divided by this, and I'm going to use the product rule and everything like that. Sure. But we could also recognize, hey, f of t being the natural log of t cubed e to the negative t is, by properties of logarithms, natural log of t cubed plus natural log of e to the negative t. Natural log of t cubed is 3 natural log of t. Natural log of e to the negative t. Oh, remember, natural log and e cancel out. So we're going to be left with negative t. So we just have 3 natural log of t minus t. That's a simpler way to write that function, in my personal opinion. And now, f prime of t will be 3 over t minus 1. Ain't gotta be complicated. let's see. Is there anything else we want to talk about now? Yes, there is. We mentioned other bases for the exponential function. So we talked about e to the x, and then we said, okay, now what does that tell us about a to the x? Here we've talked about natural log. But remember, natural log is natural log of x, is log base e of x. So what about log base a for all the other possible choices? Turns out, just like when we talk about the derivative of a dx, it's going to be very similar to the derivative of natural log with a little conversion factor as the price of working in base a instead of base e. So let's figure out what that conversion factor should be. In fact, I've actually not seen this done in any other math book, and it's not in yours. I just did it myself because I'm a strong independent mathematician who don't need no textbook, and I think it's slick, so we're doing it. Suppose, sorry, this is an example. So other bases. Let's suppose that log base a of x is equal to y, right? We can always write that. We're just going to say, hey, call this thing y. Well then, if I want x by itself, I would exponentiate both sides with a as the base. A to the log base a of x is equal to a to the y. That and that cancel out when they're exponentiated, so x is equal to a to the y. That's just the definition of the logarithm. Now, if I take the natural log on both sides, moving into natural log of x territory, natural log of x is natural log of a to the y, which is y times the natural log of a, but what was y? Y was log base a of x. So, natural log of x divided by natural log of a is equal to log base a of x. We've rewritten our original log base a in terms of natural logarithms. Turns out the conversion factor, the price you pay, is dividing by the natural log of a. And so that'll pop out on our derivative as well. Because that's what scalar multiples do. They pop out. So, the derivative with respect to x of log base a of x is the derivative of natural log of x divided by the natural log of a. Natural log of a is just a number, so we have 1 divided by the natural log of a times derivative of natural log of x. That's 1 over x, so we're left with just 1 divided by x times the natural log of a. Nice. Little conversion factor of natural log of a, 1 over natural log of a in there. I don't think that should be surprising, given how the conversion from e to the x to a to the x worked. But it's a nice little fact. And let's try it out. Let's compute derivative with respect to x of log base 3 of x and the derivative with respect to x of log base 7 of x squared plus 1. Alright. ddx of log base 3 of x, we're just directly applying this formula with a equal to 3. 1 over x times the natural log of 3. Done and done. How about the other one? Just like we had the chain rule for the natural logarithm, and it said, oh, it's the derivative over the original thing. Here, exact same thing. Plus this conversion factor to working base A of 1 divided by natural log A. So the derivative of log 7 x squared plus 1 is derivative with respect to x of x squared plus 1 divided by x squared plus 1 natural log of 7. Derivative of x squared plus 1 is just 2x. So it's 2x divided by x squared plus 1 times the natural log of 7. And don't be scared by that natural log of 7. It's just a number. A bad number. A number I would never want to write out by hand. But just a number. And on that note, I think that's all for this week. And have a great rest of your day. And then next time, we'll be moving along to something completely different. Bye then.